ever since we could look up, we've stared at the stars and dreamed about going there. It's this profound, ultimate voyage, right? One of our grandest challenges. But is it just a dream, or could it actually be our future? Well, what we're about to explore is a roadmap, a real plan that suggests the path to the stars is finally within our technological grasp. So let's dive in.
You know, for the last 60 years or so, we've been sending these amazing robotic explorers out into the cosmos. I mean, think about the Voyager probes, launched way back in '77. They showed us the wonders of our own solar system and are literally the first things we've ever sent into the space between the stars.
But here's the catch. As incredible as they are, our probes are slow. I mean, painfully slow on a cosmic scale. Voyager 1 is cruising at less than 0.006% of the speed of light. And that's because of a really basic problem. They have to lug all of their fuel with them. The very thing they need to go faster also makes them heavier and harder to push.
Okay, so let's try to wrap our heads around that. Let's forget about distant galaxies for a second. Let's just talk about our next-door neighbor, the closest star system to us. How long would that trip take with the best rockets we have right now?
100,000 years. Yeah, you heard that right, 100 millennia. That is the brutal reality of chemical rockets. It's what's called the tyranny of distance, and it basically means that with the tools we're using now, the stars are, for all practical purposes, completely out of reach.
Our solar system is like a tiny, lonely island in a vast cosmic ocean. The closest star system to us, Alpha Centauri, is more than 25 trillion miles away. Our rockets just weren't built for that kind of marathon.
And this brings us to a really critical point from Philip Lubin, the scientist behind this roadmap. He puts it pretty bluntly. We either have to come up with a completely different way to travel, or we just have to give up the dream. Sticking with what we've got now is a total dead end.
So what is that radical new way? Well, it means we have to stop carrying our engine with us. It means we have to learn how to ride a beam of light.
And this chart shows you exactly why. It's all about the massive performance gap. Down there on the bottom right, you've got chemical rockets. They're heavy, they're slow, they're stuck with the energy you can get from burning chemicals. But up on the top left, that's electromagnetic acceleration. It's what we already use to get tiny particles close to the speed of light. The difference is just enormous. The goal is to figure out how to apply that top left power to something bigger.
So here's the big idea, the huge mental shift we have to make. Instead of a giant rocket hauling its own fuel, I want you to picture a tiny, feather-light probe that has no engine at all. The engine, the real powerhouse, stays behind, here near Earth, and pushes that little probe with a focused beam of energy. We are literally talking about swapping heavy and slow for lightweight and mind-bogglingly fast.
All right, so how does this whole thing actually work? Well, this new kind of propulsion system has two main parts. You've got the driver that creates the push, and the sail that catches it.
First up, the driver. And no, this is not one giant laser like in a sci-fi movie. This is a huge array, maybe kilometers wide, made of tons of smaller lasers. And here's the clever part. They're all phase-locked, which means they fire in perfect unison. Their light waves all add up to create one single, super powerful and steerable beam of light.
And this is basically how it works. You have one little seed laser that provides the light, and then that light gets split and sent into millions of separate amplifiers. Think of it like your computer. Instead of one giant, slow processor, we now use many small, fast ones working together in parallel. It makes the whole system scalable and much more practical to build.
And here's the part that really gets me. This is not science fiction. The core tech is already here. This little green box is a kilowatt-class laser amplifier. They exist today, and they're getting more powerful and cheaper every single year, kind of like a Moore's law for light. The building blocks are on the shelf.
So what about the other half, the spacecraft itself? It's called a wafer-sat, and I want you to forget everything you know about spacecraft. We're not talking about tons of metal. We're talking about an entire spacecraft, cameras, sensors, communications, everything, all baked onto a little silicon wafer that weighs just a few grams. And it's attached to a meter-wide sail that's designed to catch that laser beam. Now, this sail is an absolute marvel of engineering. First off, it's not a solar sail that just catches the gentle sunlight. No, this is a hyper-specialized mirror. It's built from these super thin layers of material that are perfectly tuned to reflect the exact color of the laser light hitting it. We're talking over 99.99% reflectivity. So instead of absorbing that intense energy and melting, it just turns almost all of it into pure push, pure momentum.
Okay, so you combine that incredibly powerful laser driver with this tiny, perfect little reflective sail. So what? What's the payoff? Well, this is where it starts to sound like magic. The target speed for one of these tiny gram-scale probes is over a quarter of the speed of light, 26%. Just let that sink in for a second. We're not talking about a tiny fraction of a percent, we're talking about a significant chunk of the cosmic speed limit.
And here's what that speed means in practice. That journey that would take Voyager 100,000 years to make, a wafer-sat could do it in just 20 years. This tech takes an impossible, multi-generational journey and turns it into something that can happen within a single human lifetime.
And if you want an even crazier way to think about that speed, a probe traveling this fast could get to Mars in about 30 minutes. Yeah, a trip that takes us months right now would be over in less time than it takes to watch an episode of your favorite show.
Now, of course, accelerating anything to these kinds of speeds requires a truly staggering amount of energy. The source paper actually points out that even a 1 kilogram probe moving this fast would have the same kinetic energy as a large nuclear bomb. It's a stark reminder of both the incredible power of this system and the serious challenges of dealing with things moving at relativistic speeds.
So I know what you're probably thinking. This all sounds unbelievably ambitious, maybe even impossible. But it's not some crazy all-or-nothing moonshot. There's a real, practical, step-by-step way to get there.
The roadmap is really smart about this. It's incremental. You start small, right? With tests on the ground, then simple little experiments in orbit with CubeSats. Each step proves out the technology and can even do useful science along the way. You just build bigger and more powerful arrays over time, eventually working your way up to the full-scale system you'd need for an interstellar shot.
And this part is absolutely critical. The photon driver isn't just a one-trick pony for sending probes to other stars. This exact same technology could be used for so many other things. We're talking planetary defense, nudging asteroids out of the way, or beaming power to our spacecraft all over the solar system, or creating super high-speed communication links. You could even use it to help search for extraterrestrial intelligence. The investment would have payoffs across the board.
So what this roadmap really does is it takes interstellar travel out of the realm of pure science fiction and turns it into an engineering problem. A massive one, for sure, but a solvable one. It lays out a path. And that leaves us with one profound and really exciting question. If we decide to build it, if we take this journey, where should we go first?